Hello and welcome to this quick look at bond connectivity in organic structures. It's just a quick guide really, so I'll stick to alkanes, cycloalkanes and alkenes. This refers to making sure that the solid line used to represent a covalent bond actually sits between the right atoms. So if we take this representation of ethane, obviously the solid line between the two C atoms shows that they are covalently bonded. And the solid line between a carbon atom and a hydrogen atom shows that they are covalently bonded. So obviously from time to time you might see it represented like this. This is a methyl propane. So the solid line between the carbon, the middle carbon there, and the CH3 group clearly shows a carbon-carbon single bond that exists between them. You could also represent it like that as well. However, sometimes what happens is you see it drawn like this. Now, this is actually incorrect because this appears to show that the carbon in the main carbon chain is actually bonded to a hydrogen. That's not possible because that hydrogen is already bonded to the carbon in the CH3 group. Hydrogen can only have one bond because it's only got one electron, so this isn't chemically possible. So you've got to be quite careful how you orientate your bonds, a bit like this. In alkenes, this problem can arise as well. So at A level, it's always a good idea to try and get into the habit of drawing an alkene out with 120 degrees right the way around the carbon-carbon double bond. So in this example, on the left-hand side, it's obviously correct, like we saw before. And it's got one correct bond on the right-hand side, but it also is implying that there's 180 degrees between the second carbon in the carbon-carbon double bond and the CH3 group on the right-hand side. That's obviously wrong, and neither is that bond 90 degrees. So the correct way to draw this would be something like that. So in alicyclic compounds like cyclohexane and cyclohexene, it's a good idea to try to attempt throughout to include the 109.5 degree bond angle, which is obviously present, and also the correct drawing of the 120 degree bond angle in the case of cyclohexene. These are still fine. The right atoms are shown as bonded by the solid lines. There's no inadvertent bonds between a carbon and a hydrogen that shouldn't happen, for example. Now these ones are from the same paper. So let's have a look. Where's the problem? Well, what's happened is the CH2 needs to be aligned so that the carbon atom on C double bond C is shown as properly bonded to the carbon on the CH2. And the one that's highlighted in blue, what's going on there is the CH3 needs to be moved to the left a few spaces so that the carbon lines up with the left-hand side carbon on C double bond C. So if here's my highlighter here, this carbon needs to be lined up with this carbon. This carbon needs to be lined up with this carbon. This carbon needs to be lined up here. And this one over here needs to be lined up with this carbon. So a skeletal formula usually solves this problem. But what if you're told by the question to use displayed formula? You then have to revert back to the ones you've looked at before and make sure that your atoms line up properly. Now, skeletal formulae themselves can sometimes cause confusion. It's really important to make sure, particularly if you've got substituents, that you actually have the bond in there. So the highlighted bond is a C single bond bromine, and it needs to be in there to represent the skeletal formula of these compounds correctly. So if I drew the displayed formula of the second compound, which is 1-bromopentane, you can see that the highlighted bond in the displayed formula matches the highlighted bond in the skeletal formula. Okay, I hope this has been a useful quick look at how to draw bonds correctly in organic structures. Thanks for listening. Until next time, see you soon.